Welcome, everybody. Today, I'd like to welcome you to our session on data spaces enabling city digital twins. This is a very exciting topic brought to you by the Gates Center. Today, we have presentations from Sylvia, Desalava, Anders, Nicola, and Vladimir. And I'd welcome all my panelists here today. And we've been working on this session, putting it together, and we're very excited to present it to you. So I'm going to kick off with my short introduction to kind of set the scene. So I'm just going to share my screen 1 second now. Okay. So we're talking about data spaces enabling city digital twins. And what all this comes about is the vision of our world to be able to create these smart environments, smart cities, smart buildings, smart water, smart energy. And what we really want to do with here is to use ICT to optimize the efficiency, the effectiveness of our world. This is of critical importance today. When we looked at COP26, what we see is our world is using resources in ways that is fundamentally unsustainable. ICT can be one of the solutions that help us to be able to improve those efficiencies, to maximize the use of our resources, and also to minimize wastage within our system so that we actually can create a sustainable planet. This is probably one of the biggest challenges that we possibly have. When we look at a city is a microcosm of our entire planet. It has everything that we have to do as a society, everything from education, mobility, food, health, well-being, quality of life. The city, if we can master this and make our city sustainable, it's a key step for us to be able to do this as a society as a whole and to create a sustainable world. The key technology that we're talking about today is the use of digital twins. If you're not familiar with digital twins, what they do is they help us understand the real world. By looking at the Internet of Things and various different devices that we can put into the environment, we're creating streams of data that give us insight and visibility into how the real world works. We can do this through sensing technologies and IoT. And the challenge that we have is how do we bring all of this data together to be able to observe the world, to be able to orient ourselves, to create a digital twin, a digitalization of the physical assets that we're trying to manage. Once we have this digital version of the world, we can study it, we can analyze it, we can understand how best to optimize it, what changes, what actions we need to make. We can make these real-time decisions, and then we can actually enact those decisions in the real world by going back to our actuators and changing the actual way the world works. This is the vision, this is the hope of digital twins. And within the city context, it's a very, very significant challenge. But when we actually want to build digital twins, what are the challenges that we have? Well, as computer scientists and technology providers, we understand that the information that describes all of these different aspects of our world are created in different information systems. In the example of the connected car, we can have information systems on the smart infrastructure around the car, so things like traffic management, EV charging stations, emergency services, information about the road and its performance. We can also have information about the people that are in the car and understanding what kind of information they need. So navigational aids for people that are trying to get to a destination. We can also give personalized content to people in cars as well, whether that's for a business person going to a meeting, providing them with the information that they need for that meeting, or helping a parent entertain their kids in the back of the car by directing appropriate entertainment content to them. And all of this creates opportunities for new value-added services, things like fleet management, usage-based insurance, and optimizing the overall flow of the information. The challenge that we have here is that we need all of this data to be able to make these intelligent decisions. But the problem is that all of these systems have been developed independently. They exist independently of one another, and we need a way to be able to bring them together. In the systems engineering community, they've actually studied this problem for a long time. They talk about systems of systems engineering. How do you bring together independently developed systems? And in our case, how do you enable the flow of these systems that exist within our data ecosystem to allow that data value chain to be created between these systems to allow us to build and create effective digital twins? The key challenges that we have there are interoperability. And there's been much progress in the last couple of years on the notion of protocols to be able to share data, but there's still significant challenges in terms of semantics and how we understand that data, how we use that data, and how we can more easily move data between different systems. And this is really the vision of our common European data spaces. This has been talked about multiple times in the event over the last few days, so I won't dive into it in more detail, but it's the vision of saying, how do we build this public infrastructure that allows us to make it easier to share data between different sectors, between different organizations, between different individuals. And specifically in this session, we're talking about how do we use data spaces to build these digital twins. If we have a data space in place, a data space for a city, how can we then leverage that as an information resource to build a digital twin to help us to observe the world, to understand how the twin of our city is working, to make key decisions of that, and to enact those changes back into the twin itself. So it's a really, really interesting and exciting topic that's bringing together two of these kind of mega trends in technology, data spaces and digital twins together. I'm really happy and excited to talk about the speakers that we have today. So Sylvia Olivia, who is the director of the GATE Center of Excellence, and Sophia, she's going to give us a presentation next that gives the big picture view of how GATE is tackling this challenge as a center and the importance of both data spaces and digital twins to it. We'll have Desalava later on that will talk about GATE and specifically some of the projects that they have in digital twins. We're going to have Anders talk about the digital twins city project in Gothenburg, and he's from Chalmers University, who's a partner in the GATE Center as well. We have Nikolai from Centef that's going to talk about some of the key enablers that we need for digital twins, time series data, which is of critical importance, databases, replication, etc. And then finally, we have Vladimir, who's going to talk about cross-disciplinary ontologies and semantic data integration for buildings, energy, electricity, a key enabler that's needed, and he's coming from Ontotext. With that, I'm going to hand over to Professor Sylvia Olivia, who is the director of the GATE Center. Sylvia, the floor is yours.
Yeah, thank you, Ed. Thank you for a nice introduction. I will share my presentation. Okay. Yes. Okay, I will present Big Data for Smart Society is the name of our Center of Excellence on Big Data and AI. We are part of Sofia University. And the project is financed by Horizon 2020, the teaming program, and co-financed by operational program Science and Education for Smart Growth in Bulgaria. So the main aim of this project is to establish in Bulgaria, it is first in Eastern Europe and Bulgaria, Center of Excellence on Big Data and Artificial Intelligence, to develop such applied research, innovation, education in collaboration with the government, industry, and society, thus realizing a quadruple helix model. And in this project, Sofia University is the coordinator, and our partners are Chalmers University of Technology and Chalmers Industry Technique, which are leading in research, innovation, and technology transfer in cooperation with and targeted to industry. So what are the focus of our center? We are following the big data value chain research on data management, data analytics, data insight, and engineering of big data system, as some of us are coming from software engineering department, and we are familiar with this. And we are working on this building capacity on different internal projects. And we apply those research in 4 application domains: future cities, intelligent government, smart industry, and digital health. So today's session is devoted to a future cities domain, where we are having a digital twin pilot project. And we are doing this in cooperation with different partners in our ecosystem, doing knowledge transfer on different subjects, and to attract talents and excellent researchers in order to create some intellectual assets and commercialize the research results. And we will build this based on the infrastructure. Those are the money coming from national funds, and we'll build this big data platform and open innovation labs for responsive research. And of course, we'll rely on data space for our research. Thanks that you already set the scene for city digital twins, which these digital twins can simulate and visualize the pulse of the city, which is quite complex system in real time. And we need a lot of data to do this. And even the different understanding of city digital twin, everyone agrees that digital twins are based on 3D models, which consist objects with geometrics and semantic information. They're built based on real-time sensor data, and they should integrate variety of analysis and simulations to be able to better design and take decisions. So to support these decisions, all this information should be available for presented to stakeholders, citizens, decision makers, experts in a user-friendly visualization of this digital twin as a one-stop shop place. And how Gate is contributing to this, we are now in a process of creating this Gate City Living Lab, where we contribute to the existing infrastructure with the last technologies, and we will collect in one of the districts of Sofia different data for air quality, for mobility, about walking, pedestrians, cycling, about the environment, the temperature, humidity, pressure, noise, and about buildings and different information which will be part of our data space and will use to our digital twin project. And we are a member of a Big Data Value Association from several years, and last year we become a member of International Data Space Association, so we are Bulgarian hub and a facilitator to one of these 8 hubs in Europe, and we are in such a role. We are catalysts for for national endeavor towards data sharing and data spaces. And we see us as a driver for the community to sharing both industrial and public data. Yeah, and in this row, we are working towards first data space in Bulgaria, city data space, where we already had in our ecosystem data from different sources. We are having a memorandum of understanding with Sofia municipality and another organization, Sofia Plan, where we are gathering data for built environment, for cadastre, for infrastructure. Also Urban Mobility Center, where we're having data for mobility in the city, Statistical Institute, where we have some demographic data. Also Meteorological Institute, where we have data from about the weather, and Environmental Agency, where we have data about air quality. So different sources of data which we integrate, and we already identify different use cases where our colleagues, Desislav and Anders, will explain more about the use cases already realized in this context. So having in mind the International Data Space Association 5 steps towards data space, we already are in steps 1 and 2, where we gather knowledge and we find different roles in the stakeholders in the data space, and we create different use cases with added value to different stakeholders. So the steps which are coming are to build or to buy the necessary components, and to following this reference architecture to design the data space in Bulgaria. And we also are supported, we have a governmental support, the National Agency for Electronic Governance. They are responsible for open data. We already are working with them and have, again, memorandum of understanding, and they're providing private cloud. So also in Bulgaria, we are having we are hosting Euro HPC and having another center of excellence with HPC. So the infrastructure and the technologies are here, and now it's time to work more with the ecosystem and better use cases with added value to stakeholders. And yeah, to finish, yeah, the last slide about our ecosystem. Something happened. With this, I will give floor to other speakers to present the use cases and the work so far, and our partners from Syntef and Ontologies, which we're working with on interoperability and semantic enriching semantic data. So if you want to hear more information, our annual event is next week on 8th and 9th of December. So you're welcome. Thank you.
That's great. Thank you very much, Sylvia. So our next speaker today is going to be Dislava Petrova Anatova, and she's going to talk about the GATE city data space that's going to be enabling a digital twin. So Dislava, I'll pass it over to you.
Thank you, Ed. So I'm very excited to be here in this panel and at this event, and I'm going to present the City Digital Twin Pilot Project of GATE Institute. We aim to implement the digital twin as a technical solution that scales to real-world problems, as opposite to only an abstract vision that is focused only on partial solutions. First, we aim to produce a high-quality 3D model of Sofia city or of part of it, and to continue semantically enrich the 3D model in order to be used in different kind of simulations, analysis, and visualizations of built environment and urban processes. And finally, our goal is to promote the exploitation of the digital twins for decision making. Here, the technological framework for development of the 3D city model is presented. The model integrates cadastral data describing different urban objects such as buildings, green spaces, relief, etc. In order to achieve higher level of detail, we are working on enrichment of the model using orthophotos and satellite images. The core 3D model is based on a widely adopted standard like CityGML. In addition, domain-specific data models are used or specially elaborated for specific use cases. Finally, the 3D model is visualized using Cesium Virtual Globe, allowing user interaction and perception. The 3D model presented here covers the area of District Lozenets in Sofia. Continuing to integrate more data, the 3D model is enriched at neighborhood level. In addition to the buildings and the relief, we add additional objects such as green spaces and road network infrastructure. The 3D model is not only a geometric representation of the urban environment, it is mainly based on semantic data acting as a storage and a dashboard for citizens' dialogue. Our understanding is that without semantic data, the model is a person without an opinion. We are working also on several use cases in collaboration with the Sofia municipality, our colleagues from Chalmers University and University of Twente, as well as companies supporting us with data and solution software tools. The main focus is on urban planning and design and air quality simulation and analysis. The parametric urban planning is a collaborative work between GATE and Sofia Plan, which is a municipal enterprise responsible for the spatial and strategic planning of Sofia municipality. We developed together a tool that provides data-driven decision support on urban planning based on preliminary defined neighborhood indicators related to population density, access to social infrastructure, transport connectivity, etc. Investing in social infrastructure is critical to resolve the many challenges created by rapid urbanization. In such context, again, in collaboration with Sofia Plan, we are working on a use case for analysis of the kindergarten's demand, integrating demographic data and data for built environment. Air pollution is still a major health concern in Europe. People in bigger cities like Sofia tend to be exposed to higher concentrations of air pollutants. In such context, we are performing both temporal and spatial analysis of air quality. Here you can see the spatial prediction of the nitrogen dioxide during the day. The information from the sensors can be used to understand air quality at any location in the city. In addition, we are working on development of sub-city level fluid dynamics models capable of simulating the dispersion and concentration of different pollutants. The goal is to create a high-fidelity city model for identification of pollution sources and mechanisms assessing different scenarios for city development. With the help of CFD analysis, also indoor air quality and thermal comfort is simulated. The CFD model can be connected to a data measurement system, resulting in a digital twin of the indoor environment. This digital twin will be used to monitor and predict the air quality and thermal comfort score in real time. And in conclusion, I would like to make a connection between the city digital twin and data space. Dr. Michael Greaves, one of the concept's pioneers, defines digital twin as having three parts. First, physical products in real space, virtual products in virtual space, and connected data that ties the physical and virtual together. The data space enables digital twin by connecting the physical city and virtual city and providing one-stop shop for data. Trust, transparency, sovereignty, security, and added business value. So thank you, and join us at GATE Annual Forum.
Thank you very much, Desalava. Our next speaker this morning will be Anders Long. Anders is from Chalmers University of Technology, and Anders is going to talk about Digital Twin Cities, the Digital Twin City Center in Gothenburg. Anders, the floor is yours.
Okay, you see my screen now?
Sure can, thank you.
Good, thank you. So I come from the Digital Twin Cities Center located in Gothenburg, Sweden. And this is a national competence center devoted to the study of digital twins, is in particular when it relates to cities and regions. So we have 30 partners in our center. We have been working now for 2 years. We have a 5 + 5 year time span for our center. And GATE is one of our partners, I would say our main international partner. And we have very overlapping interests with the GATE Institute in exploring how we can use technology to better life in cities and take the sort of digital twin technology to the next level. So I will talk about a little bit what we do in our center. We are a quite diverse center in terms of the disciplines involved. So this comes all the way from mathematics and computer science to architecture and engineering. So it spans from the use cases and down to the basic technology. And we try to sort of push the limits in both areas. So we have very sort of applied projects going on together with the cities and municipalities. Our collaborators, our partners in the center, they come from the Swedish mainly consulting industry and the built environment, working with real use cases. For example, a recent project we studied the use of the technology that we developed for merging the ideas from architecture and engineering in creating new bridges. And at the other end, we are building a digital twin data platform and data processing and data visualization platform that supports the research in all these areas. So you see here some of these things that we are working on. The digital twin platform, that's the basis for all these projects, all these research areas. Then we have urban planning and design, architectural and structural design, digital construction. So it's about how can you use the digital twin in the construction stage of a building. So you can follow the work, you can use VR, you can use AR, you can have multi-user collaboration between people in AR space, VR space, people sitting at the office to track the progress and improve project management in complex projects. We also have a large focus on modeling and simulation. So that is a very crucial part of creating a digital twin. So you have the data as a basis, you have visualization, and you need to have interactivity, and you need to be able to ask questions. You need to be able to say, what happens if I change something, if I add something, if I add a new bridge or reroute the traffic? What will then happen to traffic? What will happen to air quality, for example? So this all relies on high performance simulation. So the mathematical modeling and simulation is there as a part. Of course, visualization and oralization, that's the way that we consume the data and the simulation results. So then it becomes important to think about how you visualize. And then you have different kinds of visualizations that targeting different user groups at the end. And then, of course, sort of below all of this is data management and all those issues related to data management. And I will mention here just a few questions. I think we will be discussing this in the panel, but from my viewpoint, these are the main challenges that I have seen in our work. So the challenges, I mean, of course, we have technical challenges in developing new algorithms, in exploring new technologies and so on. But the main challenge, I think, is it's all related to data. And there are three main challenges, and it's ownership, it's quality, and it's sustainability. So when it relates to ownership, the problem here, I mean, we talk about privacy and security, of course, they are very important, but sort of the main obstacle that we come across is actually ownership. So different organizations, they own their data, and they are very often surprisingly reluctant to share their data. So even the municipalities, maybe they paid a consultant to create the data for them as a basis for the digital twin. And then they feel that we can't just go around sharing this with everyone. There might be sort of zero implications on security and privacy, but it's still their data. They feel an ownership, and they are not giving it away for free. They want something back. They want an agreement, and so on. So ownership is actually, I think, the first obstacle, and that also relates to national databases, where sometimes or often you have to pay to get access to the data, and this becomes a real-world obstacle when you want to develop open solutions for digital twins. The second challenge is quality across disciplines. So, for example, we look at some pictures here of wind simulation. So we have some buildings, we have some wind simulation. So here you have two disciplines involved. You have sort of high performance computing, people from that discipline, experts in that discipline coming into the center, and they are doing the wind simulations. And then we have architects who want to work with the buildings. And if you look at these two groups, they have very different views on what is good quality data. So what the computation scientists, what they believe is good data, it can be completely useless to the architects, and also the other way around. So the architects might have a very high resolution, very pretty data model, 3D model of a city or a building. But if you give that to the computation scientists, they say this is completely useless, because maybe the building looks good, but there are tiny gaps, like 1 millimeter gaps between the walls, or the building is floating 0.1 millimeters above or below ground. And if that happens, then the simulation will crash. So this is just an example that different disciplines have very different views of what is good quality data. And this goes beyond data formats. So it's not a question of having different data models, different data formats, but the requirements, what should be in the data. You have a building, a 3D model of a building, and what is good for one group is completely useless for the other group. So the data is simply not there. you can regenerate it. So then you have to go back to the original sources and be able to regenerate the data for these two different groups. And this relates to the third challenge, is sustainability. If you create a digital twin, you spend some resources, or a lot of resources in building this, you get an artifact, you get a data model that is current for one day, but then what happens the next day? So you might go out and pay a consultant to create a digital twin for you, but then what happens 5 years later? You have to redo everything from scratch and pay a new consultant to give you a new artifact. So the important thing here, I think, is not the data itself. The important point here is to focus on is the process for generating the data and making this process as automatic as possible. So ideally, you have like drones flying around and you are collecting data continuously. And there are processes in place for continuously processing data and updating the digital twin. It gets regenerated every night. So those are the main three challenges that I want to point out that I have come across so far. It's all related to data. So then I leave the floor for the next speaker.
Cheers. Thank you very much, Anders. Very, very interesting talk. Our next contribution is going to be from Nikolay Nikolov from Syntef. Nikolay will talk about enablers for digital twins, time series data models, databases, and replication patterns. Nikolay, the floor is yours.
Yeah, thank you, Ed. You can see my screen now, I suppose.
I sure can. Thank you.
All right.
Nicola, you're muted.
Whoops. Okay, so thanks, Ed, for the introduction. I'll see if I can scratch the surface. It's a pretty big topic of involving very different technologies. Yeah, so data are a key driver of digital twin systems. That's pretty obvious. Data sit in the heart of gathering the data from services, physical entities, and virtual representation. And the main classes of data that are involved are the digital models of these physical objects, data about the physical entities, data about the virtual entities, the fusion data, and oftentimes we're talking about big time series data. So there's a lot of this time series data gathered from different sensors and associated with physical entities being observed. So in that context, there's a number of challenges, and some of them are related to data management. And as also Ed pointed out, data integration is a complex problem. We have the issue of determining the semantics of the different fields that are involved in the digital twin. What are how to integrate different formats, how to align data, missing erroneous values, or how to or the fact that the data are distributed across multiple sources and systems of systems, and also related to data processing and management. So there's a need for scalable data model. As I mentioned, often we have these big time series data involved and how to store them. And then in many practical use case scenarios, we have the need for the ability to recover from failures, so disaster recovery and replicating across multiple data centers. And in terms of the time series data models, again, this is somewhat of, so these would be the main, some of the main ways to represent time series are using a relational data model. An example there is a timescale DB database, which is based on PostgreSQL. The tag set data model, this is a document data model. An example is InfluxDB. And nowadays there's also multimodal solutions where one could use, for example, a multimodal database such as ArangoDB, which supports more than one data model coming together. So in the relational data model, you have obviously for a time series, you have the time, and then you have a bunch of fields. And the fields can be many types in a relational database, and they can also point to external tables that contain other metadata that are necessary for the digital twin descriptions. And these are all type of indexable. And in this case, it's very important, let's say in advance, when you're designing a system, to think about the schema um, about how the data would be stored, and this type of data model is pretty scalable for homogeneous data. And the tagged data model, which is implemented in these document-based time series databases, it's based on tags, which are strings that are indexed. This is how the data are being accessed. And then you have values, which are primitive types, such as strings, float, and integers that are stored. These are the actual values that are stored there. And in this case, you have the it's a less rigid schema, so you don't need to know in advance about the schema of the data. You can build it up through adding new tags. Yeah, so it has this more flexibility, but it's less scalable with the high cardinalities of data. And in another interesting way of representing time series or storing the time series data is how do you do it together with the digital twin data. So in multimodal databases, you typically would have a graph data model alongside the document model, and then you could store the representation of the physical entity as part of the graph model, and use the document model to actually store the time series data and directly have it associated in one place. So in other data models, that's not really possible. So in a multimodal database, you can combine the two. And finally, something about the replication. So there are two main classes of replication. So you could replicate when you ingest the data, or replicate after you have ingested data. And some patterns would be how do you copy it on arrival, or using some kind of message-oriented middleware. So for example, a Kafka broker, before you ingest the data, that would replicate the data throughout the cluster. And after ingestion, you can do it as a pass-through. So once the data are in, they directly get forwarded to another entity. You can do aggregation, pre-processing, and these incremental or complete snapshots of a database. So thank you. I hope I managed to give some context in this topic. And I give the floor to the next speaker.
That's great. Thank you very much, Nikolai. So our last speaker before we have our question sessions is Vladimir Alexev from Ontologies. Vladimir will talk about cross-disciplinary ontologies and semantic data integration for buildings, smart grid, electricity, and energy efficiency. Vladimir, the floor is yours.
Thank you. That's quite a mouthful, this title. We learned from several of the previous speakers that data management is a key topic, key difficulty when doing digital twins and large-scale data integrations. And I guess if I take from the previous presentation, Nikolai's presentation was mostly about data volume, how to store large time series. My presentation is mostly about data variety. So given that you need to integrate data from many different domains, what are good ways of doing that? And my role in Ontologies is Chief Data Architect. Ontologies is a Bulgarian software company that works on the semantic web. We are a key partner in GATE. We're also in their advisory committee representing industry. Why doesn't, okay. So what are semantic knowledge graphs and what is their relation to data spaces? Semantic technologies and knowledge graphs enable large-scale data integration, both across disciplines, but also across enterprises or data within a whole sector. And we believe that knowledge graphs are really the perfect setting for machine learning and data science. Some people call it a marriage made in heaven, because they both enable better organization and reusability of the data science efforts, and they provide a great setting for storing the results of machine learning and also for providing richer context of the data that you want to use in machine learning. Especially data preparation efforts are much improved and made reusable and repeatable if you have a semantic underpinning, a harmonized model of how you convert data. Knowledge graphs are using for structuring, storing, querying, and also for data validation using technologies like RDF shapes. Now, in data spaces, semantics is already used in a very significant way to describe data sets, users, user entitlements, rights, slices of various data sets, and so on. But if you just get access to a bunch of data sets and they don't share any sort of common model, how are you going to use them together? So I think it's also appropriate to represent the data inside a data space using semantic technologies like ontologies or data shapes. So we believe that knowledge graphs are quite complementary to data spaces. In this slide, I list some cross-disciplinary ontologies or data models in a bunch of different disciplines or domains. First of all, in electricity, you have a series of standards, CIM and CGMS. I'll talk a bit about them in further slides. In the architecture and engineering and construction domain, you have a number of standards for representing buildings and infrastructure. The first line, IFC, LOIN, and so on, this is mostly about building information management, but also management of other architectural data that is not geometries, for example, PDFs. So, for example, ICDD, the International Container for Data Drop, is a semantic description of a bunch of files and what they relate to. And this is used, for example, in digital logbooks or building passports. And there is a number of other ontologies. Some of them come from standardization bodies like CEN-CENELEC and ISO. Others come from industrial efforts like the brick schema and haystack digital buildings, which is used by Google, the real estate core that is used by Microsoft. Then on the topic of cadastral and smart city data, or what is called city information modeling, CIM, CityGMF is the most important in this domain. GeoSparkle, which allows you to query geometric data from Sparkle. GIS BIM interoperability. So one good idea is after a building is created, you take the architectural plans, abstract them to a lower level of detail and add that to the cadastre. In the domain of energy consumption and efficiency, there is a whole set of data standards and models. FSGIM stands for Facility Smart Grid Information Model. Then the next one is Open Advanced Demand Response. The largest family of ontologies is DABGEO. It covers a lot of topics in this domain, energy consumption and efficiency. And currently, this is a very strong interest for me personally, because I think it's a great input into reaching Europe's Green Deal goals. Then in manufacturing, we have in-depth standards like OPC UA and Automation ML. And more recently, coming out of the Industry 4.0 initiative, there is AdminShell that integrates a lot of this and has a semantic rendition. In transport logistics, GS1 is the standard setting organization. And there is a number of standards, EPCIS 2.0 again steps on semantics and allows you to track things through logistics chains. And then we also have generic or lighter weight ontologies that kind of bridge between these domains. SARF is one of the most well-known, but for example, WTD, which stands for Web of Things Thing Description, is also very important to enable integration between domains. Now, starting, of course, I cannot cover all of these ontologies in a short presentation, but I'll talk a bit about some of them. So this slide represents some of the standards in ICO, Architecture, Engineering, Construction, and Operation. Building Smart International is one of the most important bodies, and CEN-CENELEC Working Group 422 is another important standards body. So we have standards for defining BIM, this is IFC, for model and view definitions, for information delivery manuals. So this is what exactly information need to be covered by a certain data exchange within a certain construction project. Then you have standards for dictionaries, for data templates, for object libraries. This is a slide by CEN-CENELEC. that covers data dictionaries. And a great initiative again by Building Smart is BSDD, the Building Smart Data Dictionary, that integrates a bunch of national dictionaries and definitions about construction, quality standards, and materials, and so on. Now, this slide is from a presentation on the European Energy Data Exchange. And the standards that I will talk about in the energy domain, they come in the middle orange layer, the information layer. So I mentioned CIM and the CGMS by Ensui. I'll talk about them in a second. Then you have lighter weight cross-domain ontologies like SAREF and NGSI link data. Now talking about electricity, the Common Information Model is a series of standards by IEC, the International Electrotechnical Commission. On this slide, we see the smart grid standards map by the IEC, and CIM covers quite a large number of standards in this domain. So you have generation, distribution, consumption, distributed energy resources, IT communication, security, and a whole lot of things that need to be covered to have a reliable energy grid, especially in the context of the European single energy market. So you also have standards to cover market-to-market exchange. CIM and its derivative, the CGMS, which is by ENSUI. This stands for the European Network of Transmission System Operators in Energy. So it covers something like 10 different domains on energy resources or energy equipment, the connections, geographic information, the balance in the energy grid, both static and dynamic balance, topology, and so on and so forth. And it is modeled in UML. And out of these UML are generated ontologies in RDFS and RDF shapes in Chaco. And the newest exchange standard for CIM is JSON-LD, which is a semantic rendition. One very important subsidiary standard is the Energy Identification Code. So it's a global scheme for issuing identifiers for all kinds of energy resources and market players. It's not only used for electricity, but also for gas. So by the ENSUG. And it is a distributed issuing mechanism, just like the DNS of the internet, DOIs for digital publications, GLAI for legal entity identifiers, and the barcode and RFID standards. GTIN is for goods and services, GLN for global locations. So these EIC codes, I think, is an excellent foundation to create an European or even global energy knowledge graph, because to have a good semantic integration of a lot of data, you need stable identifiers. Unfortunately, CIM does not comply to linked data principles, even though it uses RDF. But a lot of the time, they just use GUIDs instead of more stable identifiers. Now, on the topic of energy efficiency, there's a lot of ontologies, but one of the most comprehensive is the DABGEO series of ontologies by Mondragon University. So you see the huge variety of topics that are covered in this family, from entertainment equipment in a house to the individual social and economic factors in a household or a house, to weather, to building energy storage and consumption, and so on. You see one of the domains of DABGEO illustrated here, which is energy equipment. So again, it covers a lot of different devices and so on and so forth. My final slide is about the Facility Smart Grid Information Model. It is a US standard by ASHRAE, by the ASHRAE Association. And the idea is to enable advanced demand response. In other words, communication between the electric grid and smart buildings, so that the grid can tell a building, well, look, there's a shortage right now. Could you please reduce your consumption? Or maybe even give some energy back because there are buildings with significant energy storage. And of course, this is rewarded with the attractive dynamic pricing. And the topics that are covered by the FSG are energy management, load and generation, energy metering, and it also integrates weather data, demand response, and energy usage. The final slide is an example of layering and mixing up of ontologies from this very nice paper. You see the reference on the right. So it covers all kinds of topics like sensors, quantities and units of measure, actuators, organizations, calendar events, weather. And in the outer layer, you see more complicated ontologies that cover a lot of information in a particular domain. For example, for buildings, brick and haystack and IFC, and for the demand response. Thanks, and if you have any questions, we would be glad to answer them.
That's great, Vladimir. Thanks very much. And a nice shout out for DAVGeo, which was a collaboration with Javier and Felix and myself from One Dragon. So nice to see that work there. If I can ask the rest of the speakers to put on their cameras as well, so we can have a little chat. We have about 9 minutes before the session is over. And my first question was going to be about the challenges that we have with building digital twins and using data spaces. But I think you guys have done a fantastic job of actually setting the scene. So I'm going to actually skip that question because I think we all recognize the challenge that we have here. But what I'd really be interested in, because of the expertise that we have in the room, what do you think the lessons that we've learned so far are, and how do we apply that going forward? So if somebody was sitting here and they're thinking of building a digital twin, working with a data space, maybe in a different area, not around cities, what kind of lessons have we learned so far from our experience, and what should we be doing next? And what I might do is to go to Desalava first, because she was the first presenter, and that gives the rest of you a chance to think about that question as well. Desalava, the floor is yours.
Thank you, Ed. My primary lesson is about the collaboration with the stakeholders. I think that this is the key factor for success of the digital twin and the data space. So we have a strong partnership with Chalmers University and CIT. Gate Institute is a research partner at Digital Twin City Center in Gothenburg. Thus, the building of the digital twin of Sofia and the Gothenburg goes in parallel. And the second, connection with experts and researchers working on the same topics. We are made connections with Helsinki municipality, also working with University of Twente, the new University of New South Wales in Sydney. And of course, we are working with municipalities. So in order to build city digital twin, you should collaborate with municipality. And of course, the key factor is the multidisciplinary team, because the digital twin is a complex system, and a lot of expertise is needed to be built.
That's great. Thank you for that. I think that key about connecting with stakeholders is really important. And Anders made a point of that in his presentation. So Anders, I'm going to jump over to you. And do you want to elaborate maybe a little bit more on the importance of engaging, particularly, I think you mentioned the data owners, which is a very important point from my perspective.
Yeah, I mean, I agree with Desi to engage with stakeholders. And when it comes to data, I think you can never sort of start too early to get access to the data. That's the first step. You have to get the data on your end, get access to it. But I want to add another point here, which is that there are so, I mean, especially in this last talk by Vladimir, I mean, there's so many formats, standards, and so on out there, and you can sort of be afraid to sort of touch things because there are so many. You might choose the wrong one. But my sort of message is that don't be afraid to start building. You have to explore the landscape. You have to make some decisions, which format, which model should we be using. But you shouldn't be afraid that you don't make the most optimal decision on which standard or which format to use. Just make sure that you do an evaluation and don't pick the worst one. You have to make 20 choices when you build a digital twin. Don't make the worst choice in every category, and you are sort of in a good position. And then don't be afraid to switch over to a new technology, because you have to be ready to jump from whatever you decided to work with to the next one, because a new one will come. So it's an evolving process. The ground is shaky, the ground is evolving. So don't be afraid to start building, and be ready to change, because you will make some bad decisions.
Fantastic. That's great. I can see Nicola was nodding his head there frantically in the middle of the answer to that question. I'm just going to offer the floor to him to maybe add on to that point, moving a little bit more towards the technology and how much it's adapting and changing. And what are your thoughts there? Would you like to add a little bit?
Yeah. So from the perspective of data storage, which was kind of the focus of my presentation, I guess the important factor there for making the right choice would be what's the number of or what's the scale of the digital twin is important. And that would inform the decision of which type of solution you use in the specific case. I agree very much so with the statement about that choosing the right data schemes to use, ensuring that this type of interoperability is a huge problem. But I think Vladimir can talk a little bit better about this than I can, because he had a pretty comprehensive overview of, well, I don't know if you can talk about comprehensive in that space, but a pretty good overview of different standards and like what's the landscape for that.
Sure, Vladimir, we might jump to you there then. So it struck me the amount of progress that's been made in terms of those standards, which is fantastic. I think you gave a very comprehensive overview of what's there. At the same time, it really emphasizes that the variety problem isn't going to disappear. What kind of lessons do you think we can bring from the knowledge graph community to this problem?
Yeah, both Anders and Nikki talked about complexity, and this is also, in my impression, a very big problem to what we're attempting here. And not just at the level of data standards and different exchange formats and so on, but also at the level of associations and timing of projects. And like Europe is now giving a lot of money to start building these data spaces, but there's also nascent communities. There's at least 5 associations that are relevant. There's 4 projects to build a European energy data space. Is it going to be then 4 data spaces? How are these data spaces going to interoperate? So are we talking distributed data spaces and federation between them? Or maybe a good approach would be to have distributed semantic repositories and interop between them. For example, in architecture, there's now proposals to take Tim Berners-Lee's solid architecture, which he casted for the purpose of being able to keep your own data and take your social network data with you and allow only certain people to use it. Now they won't use it for architecture as a common data environment. So there's no easy answer to this. We of course want to avoid the situation of, okay, now we have one more standard, where before we had 10, now we have 11, and what do we do with it? But yes, I believe that by making connections between standards and describing declaratively the mapping between standards, and semantic technologies are very good for this kind of thing, we can tackle the complexity.
That's great, Vladimir. So we have about 1 minute left. I'd like to thank the panelists for all their time, their insights. It's been a lot of fun. I'd like to pass over to Sylvia to maybe just say some final words to close the session as the director of the Gate Center. Sylvia, the floor is yours to close us up.
Yeah, thank you, Ed. Thank you for all speakers for all your contribution. And in this collaboration, we already are here and see here. I believe that will speed up the creation of a data space in Bulgaria, and also with the support of reference architecture of International Data Space Association and the Data Space Business Alliance, which appeared, and which is a strong support for all initiatives in the countries in Europe. So thank you very much.
If we have one more minute, we have a question from the audience. What is the implications of Amazon's Twin Maker announcement this week? Does anyone want to tackle that? Twin Maker, never heard of it.
Is anyone familiar with it? I think that's I just see the question there now. So that was from Ken Foster. So I think that's maybe some homework for us all to go take a look at that. But it's important as well that we develop European approaches as well to this problem, and looking at the diversity of technologies that we have. As Andres was saying, that there's lots of different ways of doing this, and I think this could be an interesting thing for us to study and see what lessons we can learn from that as well.
I don't know Twin Maker, but I know a bit about Microsoft's DTML, Digital Twin Markup Language. And I think that W3C's Web of Things community group and working group are very important in this regard, because the thing description standard and related standards allow you to expose a digital twin in a simple HTTP enabled manner and interact with it just using the HTTP or, let's say, CoAP, Constrained Access Protocol. So a good way of interoperation between IoT devices.
Absolutely, and connecting with knowledge graphs as well. So I think we're 1 minute over now, so I think we can pass in the session. Thank all the speakers. Thank everyone for participating today. Great insights, and look forward to working with you all in different ways and trying to realize this vision of digital twin cities and data spaces. Thanks very much.
Thank you.
Thank you.
Thanks everyone for joining.
Take care. Bye-bye.
Bye-bye.
Bye.